So let us start our another video on starting and speed control of slip ring, of induction motor. Here I would like to mention one thing, that this chapter chiefly falls under your electro means drive class. But why I have considered to deliver a lecture on this? Because reason number one, you will get a considerable amount of question coming in your get previous year get exam paper. You can observe their means presence in your previous year get paper. Sizable amount of question coming from this area. And another thing is that the which motivated me to deliver this is that this when we will do means control speed control of slip ring induction machine using slip power recovery, that technique we will find extremely helpful in understanding doubly fed induction generator DFIG, which is a very hot topic for current research. And means DFIG won't be covered in your uh, course of means electric braking, means electric drives. It should not it doesn't, in normal course it doesn't fall under that part. So but why DFIG is so important? Because gradually people are looking for uh, alternative or renewable energy sources. Now conventional sources are thermal and hydro, but wind is people are means now looking for wind, and use of wind turbine gives rise in the research interest of your induction generator, because we find that for wind turbine the nature of the turbine characteristics matches exactly with the requirement of wind means induction generator. And double, that is why we should understand induction generator, right? Now to be for squirrel cage induction motor, we can hand as well as these are applicable to slip ring also. Three different starting methods are very common, and means it's quite means have been being used in a timeless manner. One is doll starting. What is doll starting? In doll starting, you just directly connect your machine with your supply. And during starting, okay, one thing I would like to mention here, we will use that approximate equivalent circuit. Why? I will explain. During start, we know that this R2 dash 1 minus S by S at start is equal to 1, thereby resulting this factor becomes 0. So it can be represented by a solid short circuit between the terminals. Now what you have, Jx2 dash, R2 dash, Jx1, R1, and now the question of interest is here, whether we should consider it here or we can consider it here. You see, either way this branch, if you consider, now be very practical. What motivates us to consider this starting issue? That we know that during start machine is going to draw huge amount of current, and we must take care of that. We must be able to like uh, do something to reduce this amount of current drawn from our source, because this huge starting current can cause an objectionable voltage drop or voltage fluctuation in our supply if we do not take precautions, as well as it can result in blown up fuses of any conduct means connecting wires. In addition, one thing only good for squirrel cage induction motor, that due to the absence of any physical contact, there will be no sparking takes place that is proportional to the current drawn by the motor. But still, this current is no way good for us, and we have discussed that our double means what improvisation we can do with our design that I have discussed in my last video, like deep bar and double cage rotor. But still, in doll starting is that for small motor, and for like other cases when we don't want to waste power, and even in direct for direct online starting, motor starts 6 to 10% of its rated current. So if we can permit flow of that current, then it is not good to waste money on this and go for dual starting. Well, here again I am telling you, before I discuss this means before going I discuss this justification of considering approximate equivalent circuit, let me tell you one more thing, that with advent of solid state electronic system or power electronics drives, now things have become completely we are having complete different scenario for most of the machines, and starting or speed control are done in a completely different way. But uh, we cannot means totally disregard or means bypass starting this classical technique of starting and speed control, because in 50% cases, because power electronics drives are not that cost means if you consider cost, they are somewhat costly for your say someone who wants to use your means three-phase induction motor for small purpose, some small to carry out a small job, he or that organization may not be able to afford a solid state electronics drives for that. So still 50% cases people are using that old conventional technique of starting to curtail the initial installation cost. And the second thing is that here another reason that is quite important for us, that a considerable amount of question will come in competitive exam from this classical method of starting. Now coming back to the point where I started all this kind of non-technical discussion, that how or why we can consider this approximate equivalent circuit. See, your supply, you are going to supply your machine from a constant voltage source. We can assume that this V is rated voltage. Now once you consider rated voltage, your concern is how much maximum current your motor can draw. So obviously, if you consider this branch here, which is the actual case, the current that can be drawn by the exact circuit, this approximate circuit always would draw a higher amount of current. So in terms of tolerance, you are considering the worst situation. Like calculating during calculation of regulation, I told you that your pessimistic methods are sometimes good. Similarly, if you are prepare yourself for worst condition, then you can take care of something that where the situation is slightly better than what you have means anticipated or prepared yourself for. So once you consider this, then the advantage and another advantage of considering this is that it makes it very simple. So you are having I2 dash here. Now, so during starting, we can write it like T S T and TFL is equal to 3 I2 ST dash square. Here we are assuming that I1 is almost is equal to I2 dash. And so what you are getting this will be so this gives you an interesting relation that during start it is the ratio of these two current and the slip at full load power factor. Oh, sorry, full load operating condition. This is for doll. Actually, this formula is important in calculating the torque ratio with your full load torque. Right? Now, uh, you can do what? You can do a reduced voltage starting. What is that reduced voltage starting? How can we apply reduced voltage? Two ways are there. We can go for reactor or resistor starting. So let me share an image of that. Just a minute. Yes, so here we can use resistor or reactor, but what we can observe that if we use resistor, then there will be the machine means stator is cheaply inductive in nature. Therefore, the voltage drop across resistor and these will be not means there will be a huge phase angle difference between the voltage drop across the resistor branch and your well, this means machine stator. So it would be much effective. Another problem with using resistor, that is the main problem, is that considerable amount of heat will be dissipated due to that I square R T, means the ohmic loss will be high. So what we can do is that we can replace resistor by our auto transformer. So what we do in auto transformer or reactor means first we will discuss reactor, then we will discuss auto transformer. In reactor, the drop is almost like the in line with or in phase with the corresponding voltage value. So what we can get is that the IST we can write, that is x v1 by your ZSC, where ZSC is equal to right. So now the normal short circuit current without this inductor will be how much? It will be, let it be ISC, that is the starting means dual starting current, or to differentiate with this present starting current I use ISC. Also you can say it's a short circuit current. So now what you can see that IST is equal to x ISC, because the voltage is reduced by a fraction of x while x is less than 1. Now what you will have? You will have your TST and TFL. Compared to the previous equation, we will get x square ISC square IFL square into SFL. So if we compare it with DOL, then the torque is getting reduced by a factor of x square. So but as I said, during starting we try to avoid heavy loading on the machine shaft, and thereby only a small amount of starting torque is means sufficient to make the machine run from its standstill condition. And once the machine starts running, what it does, it starts building up speed, and we know that if we consider the torque speed characteristics, it is like this. Here it is S is equal to 0, here it is S is equal to SMT, and here it is S is equal to 1. So once your machine starts building up speed, this total region is unstable region, and therefore the machine cannot settle here. Machine will come and settle somewhere in this region depending on its load requirement, right? So but this side, once it reach this side slip value is quite small, and thereby offering a high value of rotor effective impedance, so it will reduce the current requirement. The same thing happens in case of auto transformer. The auto transformer starting, what we will have the same thing. The like in case of auto transformer also we will get all these formula will become applicable to auto transformer starting. Only thing is that here in auto transformer starting, due to auto transformer action, slight difference will take place in current equation, and let me show you. In case of auto transformer starting, what you will have, now in case of reactor, there was no such question of means KVA balance. But as soon as you replace the reactor by your auto transformer, what will happen? You will have, right, and thereby it becomes, so what we will have, so see, previously our IL was, for auto transformer it was XIST when we consider reactor. Now it is reduced by another additional factor, another x, and being a number that is less than 1, x always offers attenuation. So, but if we compare the starting torque, we will see that starting torque, you can do it, you will find starting torque remains same for reactor and auto transformer. So auto transformer starting is beneficial in compared to reactor starting, because reactor, like reactor, it gives you the same amount of torque, but it doesn't offer a torque profile that is poorer than what you could get using a reactor, but while it offers a further attenuation of your starting current. So that is why in your laboratory, when you will go and perform physical experiment, you will see most of the cases we equip induction machine with auto transformer, and this auto transformer is known as variac, and we always start our three-phase induction machine using variac. And the last one is our start delta starting. In start delta starting, what we do is that I have already discussed the advantages of starting it in star and delta. What we do, we start the motor in star condition and then switch it back to delta condition. So the motor, once the motor starts building speed, it becomes capable of taking higher value of torque. Here, where is that? Yes, you can see this diagram. I have already discussed that regarding starting value and starting current, that line current, star line current is star is giving a considerable amount of reduction in terms of line current. Here, unlike the previous diagram, here the line current is considered. That is why you can see even at highest value of star connection, when the sleep is actually it is somewhat, this diagram has a little error. This side it will be actually this is the value of sleep, right? And also speed is percentage of speed, it is not percentage of speed, rather the percentage of sleep. So when sleep is 100%, means sleep is equal to 1, at that time the star connection draws maximum current. but that is also less than the line current. Now you can see here that in star connection, what we do is that we first start the machine in we connect the stator in star mode, and once you can see that these three ends are shorted using this bar, and this side is already in supply. And once the machine build up speed, what we do, we just change this switch to, we connect it from position 1 to position 2. And once we connect it to position 2, the stator winding forms the delta, and thereby it enhances the machine current carrying capability, and also the total power rating of the machine gets changed by 3 times, because for same voltage operation, if you replace a star winding by equivalent, not equivalent but delta winding, where the phase element remains same as it was in your star connection, the power will become 3 times of its previous value. And similarly, you can see that starting torque, that is also a case, that starting torque with star is 1/3 of the starting torque with delta. Anyway, you can find many numerical problems, and it should not be a big deal for you to understand it. Now, while in case of starting of wound rotor induction machine, what we can do is that is all these starting method of slip ring induction motor are applicable to wound rotor. But in addition, what we can do is that we can alter, there is a flexibility wound rotor induction machine offer. You can add an additional rotor resistance. You can connect, because wound rotor rotor circuit is accessible from external machine, means external operator, it is available to external operator. So what we can do is that we can change the setting of wound rotor machine. Here you can see that this is the case. At the instance of start, we place these brushes to short the slip rings with this resistor to short them. As soon as the machine starts building up speed, we allow a motion of this rheostat setting in this direction. So when the machine builds up means considerable amount of speed and slip becomes less than SMT, we can short this. Now the advantage is twofold, because as all these resistors are located outside of your main machine, outside of machine enclosure, they are not means contributing or means affecting or altering the temperature of your main machine, because this resistor assembly are means outside of your machine. And another important thing is that once you cut them, means once the resistor means speed builds up, you can easily cut them out of your circuit, and they will give you a considerable amount of means like considerable energy saving during normal run, because in normal running condition your rotor will behave like the rotor of a normal squirrel cage induction motor with small resistance value, but during start you can offer a huge starting resistance, thereby you can have an improved starting torque and reduced value of starting current. And both are proportional to both are interrelated, not proportional, but both are interrelated. Now see, another thing that is very interesting to note is that now consider speed control of induction motor. Now we will consider both of them like squirrel cage and slip ring. In case of squirrel cage, we do not have many options in our hand. What are the options we are having in case of squirrel cage? One is that we can vary frequency, thereby varying synchronous speed. So frequency variation is one option. Another option is voltage variation. Third option is number of pole variation. These three can be done for squirrel cage. For slip ring, these two can be done. For squirrel cage, one more can be done, that is V by F control. In case of wound rotor, in addition to these 2 and 3, this one is not applicable for wound rotor. On rotor machine it is not possible. Here you are having 5, that is variation of rotor resistance and reactance. And 6 will be slip power recovery. My objective is to discuss slip power recovery at a length and just highlight the remainings. One problem, like although our induction machine offers a torque profile that is quite similar to DC shunt motor, but unfortunately in case of DC shunt motor, quite easily we can get a linear speed variation by varying armature voltage, but in case of your synchronous induction machine, this is not so easy. The things are not so easy. Why? Let me show you. Where is that car? Here you can see that for voltage variation, actually the problem is that with voltage it is, if you recall the torque equation, it was square of that voltage. However, in case of your means DC machine, in constant frequency means flux operation, it is below base speed. As long as you can vary the voltage till base speed, base speed occurs at rated voltage, you will see that with voltage your torque variation is almost, means torque is like torque variation doesn't take place with voltage variation. In the, when you keep on increasing the voltage, only power linearly changes from 0 to the maximum value. And once the maximum voltage reach, then you again change the field flux and you get the speed control above base speed, but your that affects your torque profile. So in case of DC machine, the torque remains constant from 0 to this final stage, because the basic fundamental understanding of a DC machine lies on the fact that if you vary voltage, it doesn't alter the steady state means armature current. The reason behind this difference between DC motor and induction motor is that in DC motor it relies on generated voltage, dynamically induced voltage, and in case of your induction motor, the operation depends on means transformer EMF. So that is why these things there is a change, and here this one the torque is variable with voltage, which is not desirable, and therefore if you reduce the voltage you can see there is a means objectionable drop we can observe in our torque profile, but for that our speed variation is very small, and although that is not in linear fashion, and if we further reduce the voltage it may happen that our means one further step reduction will means bring our machine fail to drive the load. Say in if you further reduce you may get something like this. So therefore voltage variation is not a good choice. And another problem is that with voltage, this variation of torque is not desirable, because people look for, even if we vary our speed, quite often we look for constant torque. Now, in case of frequency variation, there you can change the speed anyway. Oh, sorry. Although the card will look like same, but this is a different one. Yes, here you can see that for frequency variation, maximum torque locus remain almost constant, and with frequency you can have different speed value as well. But there is another problem, like if we do it, it may causes for if we change V by F, then it will cause undesirable effect related to our magnetic circuit, because abrupt change in V by F will lead to an abrupt variation of flux, and thereby flux means changing flux will cause torque pulsation, that is also not desirable. So what is the solution? We go for V by F method. So what we do here is that we go for V by F control. The advantage of having V by F control is that it gives us almost constant flux through our entire operating region, and thereby it gives us good means top speed characteristics. So instead of having frequency variation, curves remain almost same, but the torque pulsation is not there in V by F control. Right. Now, in consequent pole changing technique, what we do that is applicable for squirrel cage induction motor only. It is not suitable for slip ring, because in slip ring it is not possible to design your system to have multiple poles. But in case of slip ring, what we can do is in case of squirrel cage, uh, as the rotor winding can take any number of pole, can adapt itself, it's free to adapt itself to any number of pole. So we can do some manipulation with our winding. Here you can see that what is happening here when we are having this is the configuration that gives us two pole structure. See, all these are for one pole, right? One segment for one pole. It is like if you want to understand, it is like having your six uh, conductors. 1 2 3 4 5 6, yeah, 6 conductors, and each of them are connected to give us a two pole. Like if we go for this kind of 360 degree, what we are having here is that, like uh, say one conductor, they are designed for 120-degree pole pitch. So with that we can have 6 pole means configuration. Now here, although it's difficult to make you understand with this small number of rotor stator winding conductor slot, but you can understand that when we change it this to this way, like just change the interchanging, then what's happening here, that everything will form for P. So once you reduce the number of pole, then what you can have, it is ns is equal to 120 m by P. So if you switch to smaller value of P, obviously speed will increase, but this method is not very good because this is a kind of sharp change, and means course change you can find like in steps for say you are having you started with 8 pole. For that you are having 750 rpm, then you designed it for 4 pole, so you will get 1500 rpm. So this is a sharp change, there is no intermediate steps. That is the drawback of our pole changing technique. Now in case of our slip ring machine, what advantages we have in case of slip ring machine? So we have covered already 4, but in case of slip ring machine, what we can do is that we can vary the rotor resistance and reactance. How the variation of rotor resistance and reactance will do or will help us to realize different value of slip. Let us see when we introduce rotor. Yeah. So you can see here that, as I have mentioned, that if you keep on increasing rotor resistance, the terminal value is R means 21 is means this R23, this as long as your R2 is magnitude wise, magnitude of R2 is less than is equal to x2, you can have your maximum torque occurring in this region. After r2 is equal to x2, your maximum torque will, you will get your maximum torque in braking zone, right? So for r2 is equal to x2, maximum torque during starting. And now if you increase the value of R2, here you can see that we are having a wide range for our torque variation. This is commonly used for low cost solution, providing low cost speed regulation, typically in kind of fan type of load, when we need to drive a three-phase motor for uh, driving an aerodynamical load. In fan type load, the torque is proportional to speed square. So you can see that it is giving us this kind of diagram. And if you increase the resistance value, then what you will have, you can have from this point, you will have this point likewise. So means this is what we can do with resistance variation in rotor circuit. But the problem here with resistance variation is that it causes a considerable amount of loss due to heating of our rotor winding. Another thing we can do is that we can vary our reactance, and if we vary our reactance, then that will directly affect the the torque profile of our machine. We can see like where it goes. Yeah. So you can see that with increasing value of reactance, what we can have, our torque will be severely reduced, and obviously there is a torque reduction. It is almost like varying the voltage, but that is also not a good approach, right? So what we do is that that is known as rotor slip power control. In rotor slip power control, what we do, right? In rotor slip power control, what happens that a cascade sets, we can do two way. One is that slip power. Let me insert the diagram, then we'll have easy. It will become easier for me to explain. Yes. This is two way we can do. We are targeting this MIM indicate main induction motor, and AIM indicate your means auxiliary induction motor. And our AIM, this indicates auxiliary induction motor. Right. Now, two way we can do is that we can take AIM is equal to in this configuration we are feeding the, or we are connecting the stator of AIM with the slip ring of our MIM. That means slip power of AIM is fed to stator of AIM, right? Just a minute, there is certain problem. So what is happening here is that the MIM represent main induction motor and AIM represent auxiliary induction motor. Now slip power of main induction motor is connected with is fed to HAN, means auxiliary motor. For configuration A, your auxiliary induction motor can be squirrel cage induction motor or slip ring induction motor. SRIM indicates slip ring induction motor. And squirrel cage induction motor is, this is possible for configuration A. Do note that both the machines are coupled with same shaft, and in another case you can have the like this slip ring, and this is also here. Unlike the previous one, the slip ring of auxiliary induction motor is connected with the main motor slip ring, and stator of auxiliary induction motor are short circuited through a variable rheostat. Right now, this is called the cascade connection of our machine. Now, think about it. Say, let us go to analysis. Let the P1 and P2 be the number of poles and F1 and F2 be the corresponding frequency, synchronous frequency of input voltage. Now consider these S1 and S2 be the slip for MIM and AIM, right? So what we can write is that for MIM, what is your synchronous speed? For AIM, now rotor speed for MIM now for do note that rotor of the two machines are mechanically coupled. That means if rotor of MIM rotates at speed of n, then the rotor of AIM is also obliged to maintain the same mechanical speed. So in terms of AIM, it will be 120 F2 by P2 1 minus S2. So from this what we can write is that n is equal to this is when the torque of the two motors are in same direction, and otherwise what you will get sorry, I just made a mistake. This is when the torque of the two motors are in opposite direction, and if it is in same direction, then obviously this holds true. Now the input frequency, if we consider here for figure A, input frequency of auxiliary induction motor is what? Is your is the slip frequency of first. Do note that input frequency of auxiliary motor is the slip frequency of main motor. Therefore, when the torque of the two motors are in same direction, then we can write 1 minus S by P1 is equal to S1 1 minus S2 by P2. From this relation, we just replace this F2 by SF1, right? Then what we can write? We can write this expression. Now that gives us S1 is equal to P2 P1 plus P2 minus P1 S2. Now slip of AIM operating with your rotor secondary, and in no load condition you can expect that slip S2 is very small, and therefore you can neglect this So what you will get, S1 is equal to P2 divided by P1 plus P2, and N is equal to 120 F P1 plus P2. And when the two motor torque is in opposite direction, then what you can get? It is 1 minus S1 P1 is equal to S1 1 minus 2 minus S1 by P2. That gives us S1 is equal to, by doing the same simplifying analysis, P2 minus P1. Clearly, if we should select in this case P2 not is equal to P1, then we will get S1 in you will get 120 F by P2 minus P1 sorry P1 minus P2, right? So if your MIM means main induction motor operated alone, then its speed will be how much? Then its synchronous speed should be 120 F1 by P1, and if the auxiliary induction motor operated with same supply, then its speed will be now. Therefore, you can have that net shaft torque is greatly reduced if we go for the differential. In differential mode, what happens? The although both MIM and AIM are connected to same shaft, but the torque generated by AIM and MIM are in opposite direction. So therefore, the differential amount of torque we can get, and that is not advantageous. So we prefer not to do that, and what we go for? We go for our like when the two motors are acting in same direction, right? This is a scheme known as slip power recovery. And see the beauty of this one, like one will solve a few problems, then you will get more clear insight. But just one thing I would like to point here, that here we draw power from slip circuit through by connecting another induction machine, and that try to means understand what is happening here in terms of physical world, that what slip power you are supposed to waste in terms of rotor heating. Instead of allowing it to heat the rotor, you are actually taking it out. Now, if you are taking it out, then what will happen? This power you are feeding to another machine that is also running to same direction, and therefore that machine tries to rotate in the same direction, and these two machines act together to share the load, and that is cumulative mode, and your speed is within means you can easily vary your speed. And what about this, like now think about the power factor improvement of my induction machine. What I can do is that if I want to operate any speed above or below the synchronous speed, what we can do is that we can inject positive or negative EMF in the rotor circuit at that particular slip frequency. And if the injected EMF is against the direction of rotor induced EMF, then what will happen? Then some portion of the rotor power input will be expanded in driving current against the injected EMF, and the speed of the motor, if you apply an EMF that is, see what I told you in that generalized theory of electrical machine, what calls say that whatever you do, the addition of the two EMFs will always remain constant.
So whenever you are injecting EMF, the total value will remain constant. Mane if you externally if you allow more means EMF in opposite to E2. E2 is the or AC2 is the induced EMF across rotor, and you means apply an EMF that is opposite to SE2. Then what would happen? That EMF will reduce the magnitude of AC2, and thereby it will reduce the flow of current through your rotor winding. But if the current flow gets reduced, then what will happen? The motor will produce less torque, and due to that less torque, what will happen? The motor will decelerate. Now if the motor decelerate, then what will happen? The S will increase, and if S increase, then there will be more EMF induced from your stator, because at that time the rotating MMF and rotor conductor relative speed will increase, and therefore your AC2 will again increase further to ensure the adequate flow of current through rotor winding, so it can cater the torque demand. And now just consider the opposite situation. If you allow or inject an EMF that is in phase with the SE2 and of same frequency, then what would happen? That same frequency rotor EMF and this EMF, they will add, and this they together will push more current through your rotor winding. Therefore the rotor will produce more torque than required. Therefore the machine will start accelerate, and as soon as machine start accelerating, your slip value will reduce. And we know that in our stable operating zone, if we reduce the value of slip, there is less torque. So there is less torque, so this will continue until the torque demand and your means machine means speed, these two are means matched. And once they get matched, then you can means by injecting this additional EMF at your rotor circuit, now you can operate your machine at the highest speed. So this is more or less the slip power injecting scheme. When we solve a few numerical problems, the idea will become clearer to us. But this is also the basic idea of DFIG. And how we can improve power factor. See that power factor, if we consider slip ring and squirrel cage induction motor. In squirrel cage induction motor, this totally an inductive circuit appears to your stator winding, through your stator winding, and totally inductive circuit appears to your supply. That is why it draws a huge amount of magnetizing current to build its MMF, so it can means drive the flux, working flux through air gap. But in case of a double fed circuit, you have the slip. So through slip you can inject some of your power to counterbalance this need, and it may happen that you apply so much power that it doesn't need much means capacitive current to be means much uh, kVAR requirement alters, because you inject kVAR through your slip ring. So when we will start a double fed induction generator, you will get more clear idea on this.